Okay, is she gonna work? Let's see, let's see. We got one up, we got one up. What about the other? Come on, my boy. Ah, hello. Hey, she works. Okay, we got this down here. Welcome to the chat room. What have we got over here? We got that. And there we go. I think that's working. Probably shouldn't be watched from that account. That's my work account. All right, there we go. Right, we're not on this one. We are much further. We're on ownership inventory 4. Yeah, I did not do well on that last quiz. Let's shut that down. Right. What are we on? I thought there was more than that. Now we're on this one, aren't we? Yeah. Right, we got two more quizzes to go. Minnesota. Bevy system, diesel queries. Oh, sorry about that. Sorry about that. I had my arm on my microphone, which is just this tiny little lapel mic. All right. Apologies to begin with. I am incredibly tired. I haven't slept in, damn, quite a while, honestly. Not going to be the most cognizant, but hey, normally I ain't anyway. Right, I'm just going to reread this quite quickly, see what I messed up on previously. Right, multiple parts, contacts, designing a simple game, yeah, asset manager. It's all come back to me, ain't it? We have, yeah. What was the first question? Once loaded, the assets should be permanently. I don't remember. Oh, yeah. This was the one where I had to choose which implementation, met the requirements. Yeah, I did not have a good time with that one, did I? 3 and 4. I said all of them were fine. Oh, no. No. The requirement was a client of asset manager must retain access to assets across several short-term borrowers of an asset manager. Oh, I can't exactly just look back up to see what section it was. I'd have to go between the two. I guess I'm really not going to go over them all again. I'm just going to go into dispatch now. Anyway, welcome everybody, if everybody is here, and by everybody I mean solo me. I'm the only one who matters, though. I am a king. Right, anyway. Bevy systems. What does that mean? Inspiration. What is this? I don't know what inspired this. Is this just like, hey, here's the specific parts of the docs that we're utilizing, or separately is this I really don't know. I can't really remember, I guess. Nonetheless, we continue. Right. I'm just gonna head right into the quizzes at this point. It's been long enough. Knock. What does knock mean? You cannot call in your own stream. I don't know. Right, dispatch. Let's read this bit. Question 1A. Question 1 has multiple parts. The box below contains the shared context for each part. Context. You are designing a simple event system that calls callback functions in response to events. An event struct provides functions to register callbacks. A callback is either parallelized, runnable across multiple threads, or sequential, must be run only on the main thread. Below are several proposed designs to implement the functionality. You have a public struct events. We have option 1. Parallel and sequential are two separate methods. Right, so we have events, which is a public. We are implementing on events, the struct, two different functions. We have register and register sequential. Right, so this is to ensure that parallel and sequential possibilities are both in a separate method, I guess. Okay, so here we have, I can't parse this. EF. Is that lifetime? I can't remember. Sure. Anyway, yeah, I can't parse that. Why can't I parse that? Right, so we are taking immutable reference to self as well as f, which is a function. I can't remember what e means in this context. Damn. I really haven't been keeping all of this information in my head. All right. So we have register, which is ef, which brings in a function. We take in a function of type f, which takes in e. Is this typing or lifetime? I think this is typing. So it can have a function of any type, or sorry, e f, apologies. F is any type that meets the boundary of a function that takes in one parameter of any type, I'm assuming? Yeah, I guess so, because that's the callback. So on event, if you register, you pass it a function, which takes an immutable reference to self, and the function, which is a callback, which must have a single input, which is of type E, I'm assuming. Now we have something very similar here. In fact, it looks to be the exact same thing. Yeah, it's the exact same thing, except unnamed. Okay, I guess the only real important piece here is that it's just two methods. I didn't actually need to read any of this, which is fine. I'm glad I did, though, to try and remember to try and parse that little bit that I couldn't, I guess. Right. Second option, parallel and sequential are two members of an enumerable. Right, public enum callback, you have parallel and sequential, which both are of type F. I don't know. Implement events, public, function register, takes in uh, the same syntax here, which takes in a callback of type F. Okay. Option 3. Parallel and sequential are markers in a trait method. Right. So we have public trait register, taking in, or with marker enf, function register, takes in a mutable reference to self, and a function of type F. public struct parallel, public struct sequential, implement register, uh, fucking hell, of type parallel F or E for events, where F is a function register, a function taking in type E, function register which takes in a mutable reference to self, and a function of type F. Okay. Secondarily, we have an implementation which is the same, where F equals a function which takes in sequential. Right, so the real difference here is not much. Right, yep, so we're really just implementing on... Yeah. I say yeah as if I fully recognize what's going on here. I'll admit I don't fully, and could not write this code myself. At all. We have implement FE, register sequential FE for events. So that is implementing on the type register of type sequential. I don't recognize this, I'll admit. Select each design option that satisfies the following requirement. A callback should be considered parallelized by default, and the API should reflect that default behavior. Alright. Two members of an enum. Right, so first off we have this, where there are two different methods. That cannot work because you have to select these two. I guess register could be thought of as that. A callback could be considered parallelized by default, and an API should reflect that default behavior. Right, I would argue that register being the default, register would be the default behavior here anyway, so I would agree that option 1 agrees with this requirement. However, that is not the API agreeing, that is a naming structure. Secondarily, we have two members of an enum. This does not work, as you would have to specify a parallel or sequential enumerable in order to actually have this work. That wouldn't be by default. Option 3 is by a trait method. We have a public trait register, function register self F with F. Right. I don't think that has a default behavior. My understanding is that you'd either have a parallel or a sequential. So I think that 1 is the only reasonable solution here, though I could be entirely wrong on the trait method. Right, I'm just going to make a quick note that I do not understand trait methods. Right, Rust. The book. This is old, when I first tried to go through it. Looks like it's still mostly correct, though. Hey. Right, so we have this. I believe that is the only thing. Right, so the next requirement, the API should export as few methods as possible. That would be this. We have number 2, obviously. Number 1 has explicitly 2 methods, and number 3 only has 1 method in the end. Different behavior, but 1 method. Register. Alright, the API should lean on the compiler's type inference system as little as possible. Huh. Huh. Type inference system as little as possible. Right. So I think that 1 does follow this ruling, as it has the same amount of inference from what I can tell as anything else. Though number 2 would be a better option for that, I'd argue personally, as that's not really inferred. I'm going to say 1 and 2, as 3 does not. I believe 3 does have quite a bit of a. No, no, I guess it doesn't. I don't understand. I understand what the question is asking, but I don't think I know. What is being inferred here? Let's go with 1 and see what is being inferred. Right, E is being inferred. F is a function. Right, that's about it. Here, though, we are creating a parallel or a sequential. What is being inferred? We have a little bit of inference here, by my understanding, but elsewise, I can't see anything. 1 and 2. Let's just go. I got 2 or 3 correct. Ooh, I was wrong about this one. But the rest were correct? I thought it was the other way around. Okay. What is the question here, and how did I get it wrong is the real thing. Can I get this without going back? A callback should be considered parallelizable by default, and the API should reflect that default behavior. Okay, I'm going to guess that the first one. Right, I guess I'm probably wrong on the first one. But option 3 may be parallelizable by default too. Right, let's see. Let's see the correct answers. The answer is 1 and 3. I was correct on that. I am surprised that they said 1 is correct. I thought that would be something that they'd say was incorrect, though it is, in my opinion, correct. Right, context. Anything that starts out with first, let's imagine, means we're going for a ride, aren't we? Let's imagine what it would look like to register a callback under each design. We have events.register, taking in E of type onClick. Sorry, God, what is it called? A closure taking an E of onClick, with a function within it. Then we have register sequential doing the same. Option 2 has a callback, colon parallel, which inside of it holds a function where E is of type onClick and a sequential with the same information. Yep. So you do have to specify specifically. And now option 3, we have events.register with E of type onClick. And it's, yeah, I see. Right. Yeah, I understand. Yeah, so we don't actually have to put in anything for sequential. Huh. Yeah, that is incredibly stupid. I hate this type of behavior. So you have to pass in an empty struct that is never used, and you specifically have to use the underscore, which any good LSP will say, okay, so this is something that we do not want to use. So just don't annoy them by saying, hey, warning, this is not used. This parameter has to be pushed in to the God, forgotten the word again, but the function we're passing in order to have it operate under this behavior. I can understand now, but I hate that type of syntax. Right, that is why it is, in this specific case, defaulting to parallel. Okay, Of these options, 1 and 3 convey that parallel is the default mode as it corresponds to the simplest option. Being sequential requires either using a longer method name, underscore sequential, or a marker type, underscore sequential. Option 2 does not clearly mark that parallel should be default because both parallel and sequential must be passed in to register. I'll admit I do prefer option 2. I think that looks nicer myself, just on aesthetics. But yeah, no. I like that. That looks pretty to me. Right. Second answer, let's still read the context. 1 and 2 are correct, for the API should lean on the compiler's type inference as little as possible. I answered 1 and 2. 1 and 2 do not require much type inference beyond determining the type of the function, f. Option 3 uses an overloading trick by requiring a register trait parameterized over a marker type. Remember, it's 2 register calls. We have events.register, function taking an e as on click, or taking an underscore as sequential, and e on click. I say again, this is incredibly hacky. I haven't said this first time, but that is incredibly hacky though. Yeah, now I kind of do understand what's going on. Right, so we're implementing register on events, which is an enum up here. And on events, we have registered if you have a function where you have registered that just takes in f, which is the function, you do whatever you would do for parallelized. But if you also have this useless piece inputted into it, you have a different behavior. I understand that now. That's incredibly stupid. You implement different behavior for the different, I keep forgetting the word for this, but the different layout, whatever it's called, for the function. I hate that so much. Oh, sorry, yeah, the function passed in. I hate that so much. That's incredibly hacky. But yeah. Option 2 does not clearly mark that parallel should be default because both parallel and sequential must, that is, of course, yes, what it stated. Right, yep. I think I understand what's going on now. Sorry if I've not explained it too well again. I'm fairly tired. Alright, we have question 1a. Context. You're designing a serialization library that converts Rust data types into formats like JSON. A serialized trait that can be implemented by serializable types, and a toString function that converts serializable types to JSON. That is functionality. Below are several proposed designs meant to implement this functionality. Option 1, type serialized to a value enum. So we have an enumerable with a string and a number with either a string or a number, which is of type isize or string. Public trait serialized, which has a function on it taking in a reference to self, outputting a value. That is the trait that must be implemented on serialize. Sorry, the function which must be implemented on the trait serialize. We have function, value to JSON, which takes in a value and outputs a string. We have a public function to JSON, taking in data of anything that implements serializable, outputting a string. We let value equal data.serialize. So we run serialize method on value, on data, allowing its output to be kept in value, and then we simply value to JSON that value. Option 2. Yep. Option 2. Type serialize via calls to a serializer interface. Alright, so we have a public trait serialize with a function serialize. With a, what is the word? I've been looking for this word the entire day and I just can't remember it. Something which could be many things. Serializer. Right. So serializer must be of type a mutable reference to S, which is any type called serializer. So any type S that implements serializer. Public trait serializer, which has two functions. Sorry, adding to the public trait serializer. No, creating the public trait serializer, which has two functions, serialized string and serialized number. The only difference between the two being it takes in a string slice or an I size. We have struct JSON serializer, which has a buffer of type string. Implement serializer for JSON serializer. There is a function there, which is unseen. Public function to JSON, taking in data, which implements serialize, outputs a string. Let mutable serializer equal JSON serializer, holding in a buffer, which is a new string, empty, of course. Alright, data.serialize, running that function. Mutable reference to serializer, then we run serializer.buffer. Or output, sorry, that is outputting serialize.buffer. I don't know why I thought run. I was looking for a function here for a moment, but no, we are simply outputting serializer.buffer, which will store the output of data.serialize. Okay. Hello, Sorbet! Glad to see you. I'm very glad you came in to watch me fail horrifically at this section of the quiz. Last time it was good, though. Sorry, I am incredibly tired right now, so I'm not going to be very helpful. Thank you for joining, however. We are learning nothing. We're just testing our skills. I am getting humbled. Right. So with all of this code, hope you don't mind, I'm just going to continue on. You started computer engineering? Hell yeah! You're going to have a massive head start. Or not. I really don't know what your computer programming or computer engineering degree is going to take on, but that is really good. I'm glad to hear, man. Right. Currently, we are going over the requirement of it should be possible to add a new data format without needing to modify code in existing implementations of the serialized trait. A new data format. Right. No Rust? My god, half a year wasted for you, Sorbet. I'm so sorry. Nah, trust me, if you can learn Rust and you can work with Rust, you can do anything. Seriously. Even C. If you're learning C, it's fine. Just break stuff. Have as many errors in your code as possible. No one will notice. That's the issue with C code. Ah. Still though. That's a lot. That's really cool. What is it in them? I'm quite curious to know. Sorry to veer off course horrifically. I'm curious what's in the course. And if you're going to answer that, I get time to read this again and remember what's going on. Function, right. So, new data format without needing to modify code in existing implementations of serialized trait. I think that the option 2 would probably be the best for this. Since we have a public trait, serialize, which is a function. Yeah, so this is just a bunch of traits, and we Python next to C++, Visual Basic? Everything else is fine. Why are you learning Visual Basic? That is insane. Is anything still using it? I have written in code bases that use Visual Basic, but why? That's insane. And JavaScript last. That's insane. That is a very weird course load. Hey, at least you'll be able to talk to the old heads and tell them that you know VB. That's, to repeat myself, absolute insanity. Hell yeah for Python though, and I'm so sorry. I am so sorry for C++. I hate that language. Right though. I think that the answer here is 2. Gee. Number one, I think that you'll have to add in new enums to the value, right? Yeah. Public traits. Where even is value utilized? You hate JavaScript, Java, and C Sharp? They look ugly? Okay, I gotta defend C Sharp here. C Sharp is gorgeous if written correctly. You are entirely correct on Java and JavaScript, though. They are horrific. Python's quite pretty, though. Python is very pretty. I love Lua, however. If you've ever written Lua code, that's quite pretty. Especially if you make it so. You're right, though. Ah, I think this does have to have the value enumerable. That's the answer. Right. So the next requirement, the process of serialization should consume as little memory as possible. Process of serialization should consume as little memory as possible. And these are the two same options. Right. Let me think on this. Let me think on this. We're creating a new string here, which is we have data, which is implementing creating a new string. That's already taken some new information. Data.serialize. What does data.serialize do? I'm fairly certain we don't have information on this. It takes a mutable reference to an S. S is a serializer, right? Which is string size. String sizes shouldn't take too much in, and I size shouldn't take too much in either. Buffer string, which is on a struct, that'll take more memory too. Doesn't seem like too much memory. Here we have a public enumerable string or an I size, which is simply being passed in here from value to JSON. Value is being brought in from data.serialize. Data.serialize is a function which takes a reference to self and returns a value, which can be either a string or a number in and of itself. Right. So this creates a new string no matter what. Where is serialized number even used? JSON serializer, data.serialize, serializer.buffer is output to the end, which is kept in. Huh. I don't think that is used anywhere. No. So I'm guessing both of these are utilized within this implementation here. That has to be the case. So the only real information here we have is that during this section, we can have a value, which is simply a number, which is an I size, or a string. All of that information is brought in by the implementer. Uh, I'm certain they do in some places, but I'm certain that there's a lot of other places where it's much nicer. I hope that they have like some coding standard or something, so at the very least they have just one way of doing stuff and don't flop around like a fish. But who knows? Who knows? Right. I'm going to say that number one should consume less memory than number two. That number two always requires a string to be created, which is not exactly a useful thing. You really shouldn't be doing that. On top of that, all of this section of memory will have to be built in. So I'm just going to say one. All right. When the same data type is serialized into multiple formats, that should increase the size of the compiled binary as little as possible. I don't have any idea how to know that, I'll admit. Data type is serialized into multiple formats. That should increase the size of the compiled binary as little as possible. Right. So anything which implements serializer for serializer public. Right, what do we have? We have an enumerable, which is a value, which means that it can only take in these two pieces. We have serializable, which has a function of serialize, outputting a value, public trait. That must be a value. And it's taking in anything with influence serialize. I don't see this. I'd hate to say one twice in a row, but I don't see this changing the size of the binary dependent on how many different things are used, unless you add more to value. Enums do increase the binary size, that is correct. And this doesn't utilize an enum at all. That's the only point that I can see, honestly. Everything else. Are you certain that it'll increase binary size dependent on how many things are used? I do understand that an enumerable will, of course, increase binary size outsized to simply a struct. I can't see anything directly here either, which would increase the binary size dependent on many different things being serialized, however. So I'm just gonna have to say 2. Sure. I got nothing right. Not a single thing. I'm okay with that. The things that were saying that you wouldn't use enums were for mostly flexibility by my memory. Though I just got 0 out of 3, so my memory isn't great. Hey, it's actually not that bad. 2. So it's the opposite of what I thought. It should be possible to add new data without needing to modify the code and existing implementations of the serialized trait. 1 and 2? Both can do this. Without needing to modify the code existing implementation. In existing implementations, I'm an idiot. Okay, I'm an idiot. I thought it meant in here. I thought it meant within this code. Yeah, of course you can just add a new value within the enumerable here, and anybody already using the enumerable will have a perfectly fine time. That'll be okay. Both designs are sufficiently decoupled such that new data format is independent of any serialized implementation. For option 1, each data format converts a value into a format's representation. Value acts as a module boundary. For option 2, there is no explicit intermediate representation of a serialized value, but rather each serialized implementation is explicitly generic over any choice of S that implements serializer. Okay. That one I did misunderstand. Doesn't stop me from that. I am still an idiot, to be clear. Oh, I just got this entirely incorrect on this one. 2. Consumes less memory. Option 1 serializes data by first converting a data structure into an intermediate representation value, which will take up memory, and then converting value into the final format. The intermediate data structure consumes memory, which is not needed by option 2, where data is converted directly into the final format. Right, and my reasoning here, by the way, to be clear, that buffer string new is going to take up more memory than simply the one scenario where it's an I size. By my understanding, I size will be 16 bits. whereas string new will be upwards of 128, though likely 64. No, it'll be 32. No, it'll be 16 normally on a Windows standard, or 8 normally on a Unix standard, usually holding a secondary little byte of buffer in between the two, by my understanding. But that's nothing compared to using this intermediary, which will double the amount of memory. Okay, yep, that is incorrect. I can understand why now. I've learned something. Alright, the third and final one, I got the exact opposite of being correct, too. With option 1, there's only a single instantiation of serialize that converts a type T into a value. Because option 2 is generic over serializer S, then every time T serialize is called with a new S, the Rust compiler will monomorphize a new instance of T serialize, which would increase the size of the binary by comparison to option 1. Don't be sorry, I don't understand what the context means. Right, with option 1, there's only one instantiation of serialize that converts a type T into a value. Because option 2 is generic over serializer S. Every time. Okay, Rust compiler will monomorphize a new instance of T serialize, which would increase the size of the binary by comparison to option 1. No, I still don't understand what that means. That's okay, though. Alright! Oh! Let's go back and look at how horrific I did. Just for context, how little I understand so far, I got 1 out of 3 on the first, with a horrific answer on this second one. I got 1 out of 3 on the second one. Woo. I got 2 out of 3 on the third one. That's a passing grade for a single quiz. And I got 0 out of 3 on the last. So that is in all 1, 2, 4, 4 out of 9. Sorry, 4 out of 12. That's not even 50%, that's 1/3. I got 33% on this test. Huh. Honestly, I'll admit that's the first time that's happened to me. But hey, it just means I have a lot more to learn. That's exciting. Alright, I am going to just continue off into pattern matching, which is hopefully going to be entirely a reading section so that I can start feeling unduly confident in my abilities. Right, patterns and matching. That's going to be pretty simple. Patterns are a special syntax in Rust for matching against the structures of types, both complex and simple. Using patterns in conjunction with match expressions and other constructs give you more control over a program's control flow. A pattern consists of some combination of the following. We have literals, destructured arrays, enumerables, structs or tuples, variables, wildcards, and placeholders. Some example patterns include x, a, colon 3 of a tuple, and sum, which is an option holding color, colon red, which I'd assume was a new enumerable. In the context in which patterns are valid, these components describe the shape of data. Our programs then match values against the patterns to determine whether it has the correct shape of data to continue running a particular piece of code. Is this regex? I'm sorry, I don't really understand what you mean. No. Patterns and matching? No. This isn't going to be regex. Funnily enough, Rust doesn't have a regex implementation built into it. It's a crate, which is strange. So we're probably not going to learn about regex at all during this. I love regex, though. Which is a shame. I'd love to learn it. Sorry, I'd love to read it again and feel like a king. But no, this is going to be like the match expression as well as little patterns. Yippee. Fair. Right, to use a pattern, we compare it to some value. If the pattern matches the value, we use the value parts in our code. Recall the match expression in Chapter 6 that used patterns, such as the coin sorting machine example. If the value fits the shape of the pattern, we can use the named pieces. If it doesn't, the code associated with the pattern will not run. This chapter is a reference on all things related to patterns. We'll cover the valid places to use patterns, the difference between refutable and irrefutable patterns, okay, and the different kinds of pattern syntax that you might see. By the end of this chapter, you'll know how to use patterns to express many concepts in a clear way. Is there something clear about Rust? I'm as clear as the water that happens when you wash off the rust of your bike. That was not a sentence that was usable in any way, shape, and or form. I was as clear. This will be as clear to me as that sentence was to anybody who heard it. All the places patterns can be used. Patterns pop up in a number of places in Rust, and you've been using them a lot without realizing this. This section discusses all the places where patterns are valid. Match arms. As discussed in Chapter 6, we use patterns in the arms of match expressions. Formally, match expressions are defined as the keyword match, a value to match on, and one or more match arms that consist of a pattern. What? And one or more match arms that consist of a pattern and an expression to run if the value matches the pattern of the arm, like this. So you have match, whatever value you have, the pattern which is matched on, and the expression to run if the value matches the pattern. For example, here's the match expression from listing 6.5 half a year ago that matches on an option I32, value of the variable x. We have match x, none, we output nothing. Sum with something in it, we output sum plus 1. The pattern in this match expression are the none and sum, I, on the left of each arrow. One requirement for match expressions is that they need to be exhaustive, in the sense that all possibilities for the value in the match expression must be accounted for. One way to ensure you've covered every possibility is to have a catch-all pattern for the last arm. For example, a variable named matching any value can never fail, and thus covers every remaining case. The particular pattern, underscore, will match anything, but it never binds to a variable, so it's often used in the last match arm. The underscore pattern can be useful when you want to ignore any value not specified. For example, we'll cover the underscore pattern in more detail in the ignoring values in a pattern section later in this chapter. Conditional if-let expressions. In Chapter 6, we discussed how to use if-let expressions mainly as a shorter way to write the equivalent of a match that only matches on one case. Optionally, if-let can have a corresponding else containing code to run if the pattern in the if-let doesn't match. Listing 18.1 shows that it is also possible to match if-let, else-if, and else-if-let expressions. Shows. Oh, yeah, okay. Doing so gives us more flexibility than a match expression in which we can express only one value to compare with the patterns. Also, Rust doesn't require that the conditions in a series of if-let, else-if, else-if-let arms relate to each other. Oh. Okay, well, yeah, I don't see how Rust could even question that. There would have to be a weird structure to allow Rust to even question whether or not if-let, else-if, and else-if-let relate to each other. I don't know how I would guess that. Smarter people than me could probably make something up that does. The current listing 18.1 determines what color to make your background based on a series of checks for several conditions. In this example, we've created variables with hard-coded values that a real program might receive from user input. Right, so your favorite color is Tuesday and age. Self-explanatory. if let some color, favorite color. So if favorite color exists, color is equal to uh, color is equal to favorite color, and we print the line using your favorite color, as the background. Else if, meaning if this fails, if favorite color is none, which it is none, Tuesday. If it is Tuesday, which it is not, Tuesday is a green day. And it doesn't actually set color to anything. It just says Tuesday is a green day and then falls out. And it just says it's a green day. I guess you really shouldn't be working on Tuesdays. Shouldn't have a background on Tuesdays. Green is not a very creative color, so I can understand them not giving us anything. Else if, so if it is not Tuesday and favorite color does not exist, we let age equal, we let age equal age. And then run if age is under 30, using purple as the background color, else using orange as the background color. Right, yeah. And if none of these are done, we use blue as the background color. So what this is showing us is that you can make some really terrible and funky code. That's really good to see. If the user specifies a favorite color, that color is used as the background. If no favorite color is specified and today is Tuesday, the background color is green. Otherwise, if the user specifies their age as a string, we can parse it as a number, and we can parse it as a number successfully, which is done here. I'm assuming? Yeah, sure. Yeah, it'll be purple, so on and so forth. This conditional structure lets us support complex requirements. With the hard-coded values we have here, this example will print using purple as the background color. You can see that if-let can also introduce shadowed variables in the same way that match arms can. The line if-let okAge equal age introduces a new shadowed age variable that contains the value inside of the OK variant. This means we need to place the if age is over 30 condition within that block. We can't combine these two conditions into if let age equals age and age is over 30. Because age is being shadowed at, well, by order of operations, we shouldn't have age shadowed until the end of this. Yeah, we should. No, we shouldn't. Why is that an issue? Of course, we wouldn't have the shadowing, but why is this impossible? The shadowed age we want to compare to 30 isn't valid until the new scope starts with the curly brackets. That is correct, because this could be like some random thing. This could be 33, like the word, or Ape Escape 2 for the PS2, who knows? The downside of using if-let expressions is that the compiler doesn't check for exhaustiveness, whereas with match expressions it does. If we omitted the last else block and therefore missed handling some cases, the compiler would not alert us to the possible logic bug. Absolutely. Well-let conditional loops. Similar in construction to the if-let, the well-let conditional loop allows a while loop to run for as long as the pattern continues to match. In the thing 18.2, we code a while-let loop that uses a vector as a stack and prints the values in the vector in the opposite order in which they were pushed. So we have a new stack, we push 1, 2, and 3. We have a while-let sum top equals stack.pop. So every time this goes around, we pop the top, turning top into the value popped. Then we print top. At the end of each section of the while loop, top is technically destroyed. I believe that's now it's not out of scope, no, so I believe it's simply being shadowed. Right? This example prints 3, 2, and then 1. The pop method takes the last element out of the vector and returns some value. If the vector is empty, pop returns none. And of course, the non-variant will output nothing. It will stop the while loop. The while loop, yep, and that's what it's stating. We have a for loop. In a for loop, are we going back to all this? Like, I mean, I know I seem pretty stupid, but do we need to explain a for loop now? In a for loop, the value that directly follows the keyword for is a pattern. Oh, yeah, I guess since we are learning patterns again, it's just showing us all the places where patterns have been utilized. Fair, fair. Listing 18.3 demonstrates how to use a pattern in a for loop to destructure or break apart a tuple as part of the for loop. Right, yep, so we have index and value, which is simply a tuple inside of v.iter.enumerate, which will create an iterator and then run the enumerate function on it. I can't remember exactly what that does, but you know. Wait, can't I do something? Who cares? I thought there was hoverable here. But anyway. Alright, it'll print the following. A is at index 0, 1, and 2. Yep. Sorry. Where exactly is the pattern? I'm sorry, I just made a joke about me being too intelligent for all this shit, which was incorrect. Oh, a tuple itself is a pattern. I'm sorry. Yep. I would like to apologize again. I am very tired. We adapt an iterator using the enumerate method, so it produces a value and the index for the value placed into a tuple. The first value produced is the tuple 0, and then the letter A. When this tuple is well, that's a char, I believe. I can't remember syntax if that means it's a char or not, whatever, who cares. When this value is matched to the pattern index value, index will be 0 and the value will be A, printing the first line of the output. Okay? Let statements. Prior to this chapter, we had only explicitly discussed using patterns with match and if let, but in fact, we've used patterns in other places as well, including in let statements. For example, consider the straightforward variable assignment with let. Let x equal 5. Are you saying that 5 is a pattern? No. X is a pattern. Okay, sure. Every time you use a less statement, you've been using patterns, although you might not have realized it. More formally, a let statement looks like this. Let pattern equal expression. The statement, in statements like x equals 5, with the variable name in the pattern slot, the variable name is just a particularly simple form of a pattern. Rust compares the expression against the pattern and assigns any names it finds. So in the let x equal 5 example, x is a pattern that means bind what matches here to the variable x. Because the name x is the whole pattern, the pattern effectively means bind everything to the variable x, wherever the value is. What's a more complicated? Yeah, okay, so since you can utilize a tuple here, that's fine. Let x, y, and z match whatever match whatever value is placed, with 1, 2, and 3 each matching individually each part of the tuple. To see the pattern matching aspect of let more clearly, considering listing 18.4, which uses a pattern with let to destructure a tuple. Here we match a tuple against a pattern. Rust compares the value of 1, 2, 3 to the pattern x, y, z. It sees that the value matches the pattern. So Rust binds 1 to x, 2 to y, and 3 to z. If it doesn't match the pattern, it will break. You can think of this tuple pattern as nesting 3 individual variable patterns inside of it. If the number of elements in the pattern doesn't match the number of elements in the tuple, the overall type won't match and we'll get a compiler error. For example, listing 18.5 shows an attempt to destructure tuple with 3 elements into 2 variables, which will not work. Attempting to compile this code will give you this error. The exercise has type integer, integer, integer. Expression, sorry, not exercise. Expected a tuple with 3 elements found 2. Now we expect a tuple with the pattern integer, integer, integer. Found tuple, nothing. Or 1, 2. To fix the error, you can ignore one or more of the values inside the tuple using underscore or dot dot, as you'll see in the ignoring values in a pattern section. If the problem is that we have too many variables in the pattern, the solution is to make the types match by removing variables so the number of variables equals the number of elements in the tuple. Okay. Function parameters can also be patterns. The code in listing 18.6, which declares a function named foo that takes one parameter named x of type i32, should now look familiar. The x part is a pattern. As we did with let, we could match a tuple and a function's arguments to the pattern. Listing 18.7 splits the values in a tuple as we pass it to a function. So we have print coordinates, which takes a reference to x and y, where x and y equal a tuple equal to the value of i32 and i32, a reference to both values. Let point equal 3, 5, which is a tuple. Then we simply print the coordinates, passing in a reference to the point there. So x and y, we have a reference to a tuple, where x and y equal values within the 32s. Yep. This code prints current location 3, 5. The values reference 3, 5 match the pattern reference x, 1. So x is the value 3 and y is the value of 5. We use patterns and closure parameter lists in the same way as in function parameter lists, because closures are similar to functions, as discussed in chapter 13. At this point, you've seen several ways of using patterns, but patterns don't work the same in every place we've used them. In some patterns, the patterns must be irrefutable, which you have not described yet. In other circumstances, they can be refutable. Let's discuss these two concepts next. Oh, I'm going to get this question horrifically wrong. Determine whether it compiles. We have immutable v, which is vector 1, 2, 3, 1, 2, 3, 2 pieces inside of a vector, which is turned into an iterator. Let mutable sum equals 0. While let sum of type t, so every section that this is correct. Alright, so we got v.next. First off, we start with 1 and 2, I believe, that are put off into t, which is a tuple right now. Let underscore and n equal the tuple, which will be 2. Sum plus equals 2. I'm pretty certain that this will compile. Alright, and then the next piece, it'll be 4. So that'll be 6 in total. At which point, we'll get none, the while let will die, and we'll continue on. I think this will be 6. 6. Hey, I got it right. I feel like a king. Right. Refutability. Whether a pattern might fail to match. Patterns comes in two forms, refutable and irrefutable. Patterns that will match for any possible value passed are useless. An example would be x in the statement let x equal 5. Well, I guess not really useless, but useless for the use case of matching a pattern. Because x matches anything and therefore cannot fail to match. Patterns that can fail to match for some possible value are refutable. Here are some examples. In the expression if let sum equals a underscore value, then sum x is refutable. If value of a value variable is none rather than sum, the sum pattern will not match. Okay, yeah. Patterns that will match for any possible value passed are irrefutable. I would have thought that it would be the other way around, because you can refute the variable. That is irrefutable. I would argue that this should be irrefutable. I don't care that much. Who cares? In the expression if let reference to x, reference to a whatever vector of s, and then continuation equal a slice, then what? And then x is refutable, meaning that it cannot take any, meaning that it can't be. Ugh, fuck this. I'm sorry, but I hate the naming pattern here. If the value of a slice variable has 0 elements, the pattern will not match. It is refutable, meaning that it has the ability not to match. I get it now. I'm sorry. I am very tired. I do understand it now. I was very stupid. So refutable simply means that it has the ability not to match. Irrefutable means that it does not have the ability to not match. Apologies. That was very dumb of me. Function parameters. Less statements and for loops can only accept irrefutable patterns, which do not have the ability to fail. Because the program cannot do anything meaningful, when the values don't match. The if-let and well-let expressions accept refutable and irrefutable patterns, but the compiler warns against irrefutable patterns because it can never fail while using if-let. Because by definition they're intended to handle for possible failures. The functionality of a conditional is in its ability to perform differently depending on success or failure. In general, you shouldn't have to worry about the distinction between refutable and irrefutable patterns. However, you do need to be familiar with the concept of refutability, so you can respond when you see it in an error message. In those cases, you'll need to change either the pattern or the construct you're using the pattern with, depending on the intended behavior of the code. Let's look at an example of what happens when we try to use a refutable pattern where Rust requires an irrefutable pattern and vice versa. Listing 18.8 shows a let statement, but for the pattern we specify some x, a refutable pattern. As you might expect, the code did not compile. Let some x equals some optional value. If some optional value was a none value, it would fail to match the pattern some x, and it doesn't know what to do without that, meaning the pattern is refutable. However, the let statement can only accept an irrefutable pattern, because there is nothing valid the code can do with a none value. At compile time, Rust will complain that we've tried to use a refutable pattern where an irrefutable pattern is required. Refutable pattern local binding none not covered. Okay, that's a lot of information here. Wow, why? No, let binding requires an irrefutable pattern like a struct or an enum with only one variant. For more information, visit this. Option defined here, random piece, note. The match value is of type option I32. You might want to use the if-let to ignore the variant that isn't matched. I think this should be added up here. Because if somebody puts a let some x, I really doubt that they're going to want an irrefutable value. Sorry, a refutable value. Yeah, an irrefutable, whatever it is. A refutable value, yes. Wow, again, I am incredibly tired. Because we didn't cover and couldn't cover every valid value with the pattern some x, Rust rightfully provides a compiler error. If we have a refutable pattern where an irrefutable pattern is needed, we can fix it by changing the code that uses the pattern. Instead of using let, we can use if-let, and if the pattern doesn't match, the code will just skip the code in the curly brackets, giving it a way to continue validly. Listing 18.9 shows how to fix the code in listing 18.8. Right, we just put in a let, and then what happens if it fails? We just print it out. You've given the code an out. This code is perfectly valid, although it means we cannot use an irrefutable pattern without receiving an error. If we give if-let a pattern that will always match, such as x, as shown in listing 18.10, the compiler will give a warning. If-let x equals 5, and then we just have some option if it is true. Rust complains that it doesn't make sense to use an if-let with an irrefutable pattern. Right, yep. That's just a warning, saying, hey, warning irrefutable if-let pattern. This pattern will always match, so the if-let is useless. For this reason, match arms must use refutable patterns, except for the last arm, which should match any remaining values with an irrefutable pattern. Rust allows us to use an irrefutable pattern in a match with only one arm, but this syntax isn't particularly useful and could be replaced with a simpler let statement. Yeah, but I want to make mine look larger, like I'm trying to do something useful. Now that you know where to use patterns and the difference between refutable and irrefutable patterns, let's cover all of the syntax we can use to create patterns. Consider pattern matching of an expression with some type t. Which of these statements best describes the difference between a refutable and an irrefutable pattern? Right. Response. Refutable patterns make some value of a type S, while irrefutables make only values of a type T. That is meaningless then. What? Refutable? Sorry, I guess I just didn't read this. Consider a pattern matching of an expression of type T. Which of these statements? Yep, okay. Refutable pattern matches some value of a different type S. That is incorrect. Refutable patterns do not match any values of type T. That is incorrect. Refutable patterns do not match some value of type T, while irrefutable patterns do not match some value of type T. Well, refutable patterns are patterns where T is an enum, while irrefutable patterns are patterns where T is not an enum. What? I am very tired, I guess, because I just can't understand this. Consider pattern matching an expression of some type T, which of these statements specify refutable and irrefutable. Right, so an irrefutable one means that it can only be T, whereas a refutable one means that it can be T, but it can also be something else. Refutable patterns do not match some value of type T. Refutable patterns do not match any value. Okay, so this is stating that some. Only some of them. I guess this is the answer. Well, irrefutable patterns match all values of type T. Right. Refutable patterns match some values of a different type S. Right, I believe this to be the answer. Sure. Consider the following program. Which of the following refutable patterns are refutable patterns for X? Right, let X of type a reference to a vector holding a singular value, which is a tuple of type I32, I32, is equal to a reference to a vector holding in 0 and 1. Okay, so I'm guessing that this is being replaced here. Which of the following are refutable patterns for X, meaning they can fail? Does it mean here? That is the pattern, which must be matched here. Okay, I legitimately have no idea what it's asking. Consider the following program that. Which of the following are refutable patterns for X? So I'm going to just go forward assuming that it means which of these following have the ability to fail. That does not have the ability to fail. So that's irrefutable. This does have the ability to fail, but won't, and is thus refutable. This, I'm unsure. I believe this still has the ability to fail, but also holds more. I believe that is also refutable, because this can fail. If it doesn't hold X, Y, and it can hold anything else, but it can hold X, Y, it will fail. If it doesn't hold X, Y, a tuple with X, Y, if it holds 5, it's going to fail. Here and here, though, are refutable and can fail. I got one of them correct. That is wrong. What is the answer? What? I clicked that. Oh, come on. Okay, I got both of them right. Sorry about that. I did click that, right? Who cares? Right, reading context, a pattern is refutable if there exists some value of the expected type that isn't matched by the pattern. A slice does not have a fixed length, so any pattern which asserts that X must have at least one element is refutable. Okay. Alright, let's get into pattern syntax. In this section, we gathered all the syntax valid in patterns and discuss why and when you want to use each one. We have matching literals. As you saw in Chapter 6, you can match patterns against literals directly. The following code gives some examples. We have let x equal 1, We matched x against 1, 2, 3, and anything else. We have 1, 2, 3, and anything. The code prints 1 because the value of x is 1. The syntax is useful when you want your code to take an action if it gets to a particular concrete value. Matching named variables are irrefutable patterns that match any value. And we've used them many times in the book. However, there is a complication when you use named variables in matched expressions, because match starts a new scope. Variables declared as part of a pattern inside the match expression will shadow those with the same name outside the match construct, as is the case with all variables. Okay? In listing 1811, we declare a variable x with a value sum 5, and a variable y with a value of 10. We create a matched expression on the value x. Look at the patterns in the matched arms and print line at the end, and try to figure out what the code will print before running. What? Okay, sure, whatever. I'm just going to try and figure out what this will print without going any further. Sure. We have x is sum 5, y equals sum 10. We are matching on x, which is sum 5. If it is sum 50, we print got 50. If it is sum y, we print matched y, got y. It will not match y. Secondarily, we output default case x is equal to x, which is 5. Print line at the end, x is equal to and y is equal to, with x being the only value being put into into this, yeah, sure. X isn't changed at any point though, what are you talking about? That introduces a shadowed variable y. Y is being shadowed where? How is y being shadowed? I don't understand. Okay, let's walk through what happens when the match expression runs. The pattern in the first match arm doesn't match the defined value of x, so the code continues. The pattern in the second match arm introduces a new variable named y that will match any value in the... I'm an idiot, okay. Yeah, so any sum. Right, so it is matching anything with sum in it. And since it's matching anything with sum in it, the value, which is x, is placed into y. Matched. Y is equal to 5. And then it runs. But since the syntax is gone, y is, yet again, 10. Right? This is a new y variable, not the y we declared at the beginning of the value with 10. This new y binding will match any value inside of sum, which is what we have in x. Therefore, this new y binds to the inner value of the sum in x. That value is 5. So the expression for the arm executes and prints matched y equals 5. Does y outside now equal 5 still? This is some fairly basic stuff. I can't believe I don't know this. This isn't tiredness. I just didn't understand that, I guess. If x had been a none value instead of 5, the pattern in the first arm wouldn't match, and the value, it would match the underscore. We didn't introduce the x variable in the pattern, the underscore arm, so the x expression is still the other x, hasn't been shadowed. In this hypothetical case, the match would print default case x equals none. Yep. When the match expression is done, the scope ends, and so does the scope of the inner y. The last print line produces at the end x equals 5, sum 5, and y equals 10. Okay. To create a match expression that compares the values of the outer x and y, rather than introducing the shadow variable, we would need to use a match guard conditional instead. We'll talk about match guards later in extra conditionals with match guard section, which is later on. Right, multiple patterns. In match expressions, you can match multiple patterns using the OR syntax, or the pipe, which is the pattern OR operator. For example, in the following code, we match the value x against the match arms, the first of which has an OR option, meaning the value of x matches either the values in the arm. That arm's code will run. Let x equal 1 matching x over 1 or 2, printing 1 or 2. 3 will match 3. Right, so this is just a Boolean. It's essentially just like x equals 1 or 2. Sorry, x equals 1 or x equals 2. Matching ranges or values with dot dot equals. The dot dot syntax allows us to match with an inclusive range of values. 1 dot dot 7 would be anything between 1 and 7 inclusive. In the following code, when the pattern matches any of the values within the given range, the arm will execute 1, and then forward will equal 5. What? Oh, yeah, range to this point. Sorry, yep. Dot dot equals 5. That's between 1 and 5. 1 through 5. If x is 1, 2, 3, 4, 5, sorry, 1, 2, 3, 4, or 5, the syntax is more convenient for the multiple values of the OR operator. So if we did it with the OR operator, it'd be 1, or 2, or 3, or 4, or 5. Specifying a range is much shorter, especially when we want to match, say, a number between 1 and 1,000. The compiler checks if the range isn't empty at compile time, and because the only types for which Rust can tell if a range is empty or not are char and numeric values, ranges are only allowed for numeric or char values, because chars are just numbers. Here's an example using ranges of char values. We have let x equal c, match on x, a through j. Print line, early ASCII character. K through Z, print line, early ASCII character. Funnily enough, you couldn't do A through capital Z because there are certain symbols in between the the Z and capital A section. I think underscore, minus, and a few other brackets are in between it, which I think is a dumb thing to have done. Since chars are just numbers, and we are currently just literally asking for, I think it's like 62 with A or something like that, to a couple hundred, 130 or something like that. Well, it's not 130, but you get what I mean. Yeah, since we're literally just asking between two numbers, we can just do a range, or A is lesser, or yeah. You can use lesser than a greater two values for chars. I don't know why I'm explaining this. Destructing and breaking apart values. We can use patterns to destructure structs, enums, and tuples to use different parts of these values. Let's walk through each value. Destructuring structs. Listing 1812 shows a point struct with two fields, x and y, that we can break apart using a pattern with a let statement. We have state, struct point, x as an I32, y as an I32. We have function main. Let p equal a point with x and y equal to the values 0 and 7. We have let point x is equal to a, y is equal to b, and that is equal to p, the point struct here. So it equals a and b are equal correctly to 0 and 7. Both are true. Yep. Sorry, yeah. X of type A. Sure. This code creates a variable a and b that match the values of the x and y fields of the p struct. I've never seen the syntax and really hope I don't see it again, so we are creating two variables a and b here, which are equal to the variables, values x and y of a point. I absolutely hate this. This is disgusting. This is incredibly disgusting. I hate that so much. This example shows that the names of the variables in the pattern don't have to match the field names for the struct. However, it's common to match the variable names to the field names to make it easier to remember which variables came from which fields. Because of this common usage, and because of writing let point x, y, y, so I'm guessing we can just put like x, y in order. Contains a lot of duplication. Rust has a shorthand, which is just, I'm going to assume, yep, x, y, here. I'm going to skip over that. I hope I never see this. If I do, I'm coming to your home and I'm going to shoot you, whoever wrote this. Well, this actually. That's a lot nicer. I can understand why that would be useful. That's fine. The code creates variable x and y that matches the x and y fields of the p variable. The outcome is the variables x and y contain the values of the p struct. You can also destructure with literal values as part of the struct pattern rather than creating variables for all fields. Doing so allows us to test some of the fields for particular values while creating variables to destructure the fields. In listing 1814, we have a match expression that separates point values into three cases. Points that lie directly on the x-axis, which is true when I equals 0, on the y-axis, when x equals 0, or neither. Right, so we have matching point. Right, so we have a... Oh, that's why it's useful. Okay. That's why it's useful. I see. Okay, I'm entirely in disagreement with what I previously stated, now that I understand why it's useful. So the reason for this is so that we don't have to use separate intermediary values for this, right? So we're matching on P, where x equals the x of this point, and y is equal to 0. Same here, but the opposite. And then xy. Okay, I do like this. That's quite nice. That is a quite nice pattern. I do enjoy this. The first arm will match any point that lies on the x-axis by specifying that the y field matches its value if its value matches the literal 0. The pattern still creates an x variable, which we can then use in the code for this arm. Similarly, the second arm matches any point on the y-axis by specifying that the x field matches if its value is 0 and creates a variable y for the value of the y field. The third arm doesn't specify any literals, so it matches for any other point and creates variables for both the x and y fields. In this example, the p matches the second arm by virtue of x containing a 0. So this code will print on the y-axis at 7. Remember that a match expression stops checking arms once it has found the matching pattern, so even though point x equals 0, y equals 0 is on the x-axis and on the y-axis, this code will only print x is on the x-axis at 0. Destructuring enumerables. We've destructured enumerables in this book, for example listing 6.5 in chapter 6, but haven't yet explicitly discussed that the pattern to destructure an enum corresponds to the way the data is stored within the enum is defined. As an example, in listing 1815, we use the message enum from listing 6.2 and write a match with pattern that will destructure each inner value. Right, so we have a message which can be quit, move, write, or change color, each with an inherent value. We have let message, change color, equaling this tuple. That is a struct. Yeah, that's a struct, sure. Right, so we match on the message. If it is a type quit, that is the type thing that we do. What are we trying to see? From listening, and write a match pattern that will destructure each inner value. Right, on move x, y, that'll destructure it, so x and y are equal to the x and y fields in the struct for move. Here, we take in the text, which is the string, and make it and add it to the text variable. On message, we have R, G, and B, which is destructuring whatever is inside the enumerable. So these three numbers are equal to R, G, and B. The code will print change the color to red 0, green 160, and blue 255 by changing the value of message to see the code from the other arm run. What? Try changing the value of message to see the other code run. For enum variables without any data like message quit, we can't destructure the value any further. We can only match the literal message quit value, and no variables are in that pattern. For struct like enum variants such as message move, we can use a pattern similar to the pattern we specified to match structs. After the variant name, we place curly brackets and list the fields with variables so we break apart the pieces to use in the code for this arm. Here we use the shorthand form as we did in listing 1813. For tuple-like enum variants, such as message write, that hold a tuple with one element, and message change color that holds a tuple with three elements, the pattern is similar to the pattern we specify in to match tuples. The number of variables in the pattern must match the number of elements in the variable we are matching. Destructuring nested structs and enums. So far, examples have all been matching structs or enums one level deep. Matching can work on nested items too. For example, we can refactor the code in listing 1815 to support RGB and HSV, hue, saturation, and value colors in the change color message, as shown in listing 1816. We have red, green, blue, and hue, saturation, and value, which is enumerable, right? So you have a message which has change color, color. Right. So the only real difference is let message equal change color, color, which is an HSV. Change color, color of an RGB. Right, yep. So the values here are the structured in either sense. Good stuff. The pattern of the first arm in the match expression matches a message change color enum variant that contains a color RGB variant. Then the pattern binds to the three inner I32 values. The pattern of the second arm also matches a message change color enum variant, but the inner enum matches color HSV instead. We can specify these three complex conditions in one match expression, even though two enums are involved. Right? Destructuring structs and tuples. We can mix, match, and nest destructuring patterns in even more complex ways. Following example shows a complicated destructure where we nest structs and tuples inside a tuple and destructure all the primitive values out. Right, yep, so we have we have a tuple holding a tuple having feet and inches, point holding a point struct holding x and y, and a bunch of stuff that we can't read. Oh yeah, we can. Is equal to a tuple holding 3 and 10, as well as a point where x equals 3 and y is equal to negative 10. This code lets us break complex types into their component parts so we can use the values we're interested in separately. I really doubt we're ever going to see this exact syntax. I don't see any use for this. Destructuring with patterns is a convenient way to use pieces of values, such as the values from each field in a struct separately from each other. Ignoring values in a pattern. You've seen that it's sometimes useful to ignore a pattern. You can use an underscore or a ... right? Such as the last arm of a match, to get a catch-all that doesn't actually do anything but does account for all the remaining possible values. There are a few ways to ignore entire values or part of a value in a pattern. Using the underscore pattern, which you've seen, using the underscore pattern with another pattern, using a name that starts with an underscore, or using ... to ignore the remaining parts of a value. Let's explore how and why to use each of these patterns. Ignoring an entire variable with underscore if you just don't care and don't want to do anything in that case. Right, wildcard pattern that matches any value but not bind to the value. This is especially useful as the last arm in a match expression, but we can also use it in any pattern, including function parameters, that's shown in listing 1817. Yep, so we got function foo underscore is an I32 and y is an I32. Then we simply print y. We don't care about x. This would be useful for like a point that destructures into an xy shape here, or a tuple, which does the same thing. They should have shown that, I'd argue. This code will completely ignore the value 3 passed in the first argument and will print this code only uses the y parameter 4. In most cases where you no longer need a particular function parameter, you would change the signature so it doesn't include the unused parameter. Ignoring a function parameter can be especially useful in cases when, for example, you're implementing a trait where you need a certain type signature, but the function button in your implementation doesn't use one of the parameters. You then avoid getting a compiler warning about unused function parameters, as you would if you use a name instead. This works in every other language too, except poorly written ones. You can also use an underscore inside another, sorry, this is ignoring parts of a value with a nested underscore. Right, yep. We can also use underscore inside another pattern to ignore just parts of a value. For example, when we want to test only for part of a value but have no use for other parts of the corresponding code we want to run. In listing 1818, we show code responsible for managing a settings value. The business requirements are that the user should not be allowed to overwrite an existing customization of a setting, but can unset the setting and give it a value if it is correctly unset. Right, so if immutable setting value sum 5, immutable new setting value sum 10. Match setting value, match on a tuple holding setting value and new setting value. If it is both a sum, println can't overwrite an existing customized value. Anything else, setting value equals new setting value. Right. Yep, so that'll unset it too. If new setting value is simply a none variant, then it'll unset the value. Right, setting is setting value. This code will print can't overwrite when the setting is sum 5. In the matching first arm, we don't need to match on or use the values inside either sum variant. But we do need to test for the case when setting value and the other are sum variants. In this case, we print the reason for not changing the setting variable and it doesn't get changed. In all other cases, if either setting value or new setting value are none, expressed by the underscore parameter in the second arm, we want to allow this to become that. Yep. You can also use underscores in multiple places within one pattern to ignore particular values. In listing 1819, we show an example of ignoring the second and fourth values in a tuple of 5 items. Right, so we match on this in every second item. We destructure, we get a variable for it. The other ones we don't care about. Sum numbers first, third, and fifth. Right, this code will prevent, yep, the first, third, and fifth values. Ignoring an unused variable by starting its name with underscore. If you create a variable but don't use it anywhere, Rust will usually issue a warning because its unused variable could be a bug. However, sometimes it's useful to create a variable you won't use yet, such as when you're prototyping or just starting a project. In this situation, you can tell Rust not to warn you about the unused variable by starting the name of the variable with an underscore. In listing 1820, we can use 2 unused variables, but when we compile this code, we should only get a warning about one of them. This is particularly useful when you are taking a larger code base from one section and rewriting it in another language. I've not really found too much of a use case otherwise because I don't care about compiler warnings and will just ignore them until I need to utilize them. Also, this can mean that you can just have some variables that do remain unused until it hits the code base, and that's just meaningless clutter. The compiler should break it out, though. It should just delete it. Here we get a warning about not using the y variable, but we don't get a warning about not using the x variable. Note that there's a subtle difference between using only underscore and using a name that starts with an underscore. The syntax underscore x still binds the value to a variable, whereas underscore doesn't do anything. To show a case where this distinction matters, listing 1821 will provide us with an error. So you have let s equals sum, string from hello. We have an it let underscore s equals s, which has a sum variable. Print line found a string. It is a string. Then we try and print s. What's the problem with this? Oh, because it's been moved into the s underscore s. Yeah. Receive an error because the underscore s is the owner of s, which prevents us from using s again. However, the underscore by itself doesn't ever bind to the value. Now, listing 1822, it'll compile because we don't actually use it here. This code works fine because we never bind s to anything. It isn't moved. Ignoring remaining parts of a value with ... With values that have many parts, we can use the ... syntax to specific parts and ignore the rest, avoiding the need to list underscores for each ignored value. The ... Wait, actually here is a good use. I'm sorry to just pass by that. But if we are writing a piece of code and we know we want s to be moved in eventually, putting it in like this now as a placeholder can be incredibly useful. Because if we try and utilize it in a way which will cause issues, it'll tell us at that point which we try and use it, instead of simply going on and eventually actually implementing s, the sum s value here, at which point we'll find the errors later on. Okay, that is a useful piece. I can see it useful in Rust and only Rust, nowhere else. Sorry to go back. Right, that has many parts. We can use the dot dot syntax to specify parts and ignore the rest, avoiding the need to list underscores for each ignored value. The dot dot pattern ignores any part of a value that we haven't explicitly matched in the rest of the pattern. Listing 1823, we have a point structure that holds a coordinate in a three-dimensional space. In the match expression, we want to operate only on the x coordinate and ignore the values of y and z fields. Right, so we have it right here. We have point x dot dot. Pretty self-explanatory. Right. We list the x value and then include the dot dot pattern. This is quicker than having to list y underscore and z underscore. This is particularly useful when you have like 10 different values within a struct. Particularly when we're working with structs that have a lot of fields where only one or two is relevant. The syntax dot dot will expand to as many values as it needs to be. This shows how you use it in a tube. Right, so you got first, dot dot, last. Anything in between will be meaningless. You can also have last, colon, also we can have a second last, colon, last, and it'll be fine. Comma, not colon, sorry. In this code, the first and last values are matched with first last. The dot dot will match and ignore everything in the middle. However, the dot dot must be unambiguous. If it is unclear which values are intended for matching and which should be ignored, Rust will give us an error. Yep, so we got dot dot second, dot dot, which second could be anywhere. I mean, that could be the one in the exact center, 8, but we don't know that. Or it could be a 4 value one, at which point it could be 4 or 8. When you compile, we'll get this error can only be used once per tuple pattern, previously used here. It's impossible for us to determine how many values in a tuple to ignore before matching a value with second, and then how many further values to ignore thereafter. This code could mean that we want to ignore 2, bind second to 4, and ignore 8, 16, 32, or any other piece. Extra conditionals with match guards. A match guard is an additional if condition, specified after the pattern in a match arm, that must also match for that arm to be chosen. Match guards are useful for expressing more complex ideas than a pattern alone allows. The condition can use variables created in the pattern. Listing 1826 shows a match where the first arm has a pattern sum x and also has a match guard of if x is modulo 2 equals 0, which will be true if the number is even. Right, sum 4, we have match sum if x is x mod 2 is 0. Okay, yeah, that's pretty useful. I think that we've seen this before, but it's good to be reminded. I quite like this. If it matches the sum pattern, if it is anything, if it is something, and also separately, if that something is even, then print the number is even. That's quite useful. This expression will print the number is even. When num is compared to the pattern in the first arm, it matches because sum 4 matches sum x. Then the match, yep. If none had been sum 5, instead, it would fail. There's no way to express the if x is mod 2 equals 0 condition within a pattern, so the match guard gives us the ability to express this logic. The downside of this additional expressiveness is that the arms will match with match guards don't count towards exhaustiveness, so even if we add sum x, right, yep, so even if we do actually technically have every single possibility, it might still tell us that we need a, at this point, useless none arm. In listening 1811, we mentioned that we could use match guards to solve our pattern shadowing problems. Recall that we created a new variable inside the pattern with a match expression instead of using variables outside of the match. This new variable means that we couldn't test against the value of the outer variable. Listing 1827 shows how we can use a match guard to fix this problem. Right, so here we have it. Sum n. If n is equal to exactly y, we print... What? This code will if n is equal to y. Yeah, but if you still put y there with shadow. Okay, yeah, no, I see. Never mind. Yep, makes sense. Sorry. So originally the idea was that if you put some y, which is what I originally assumed it would say, hey, if it is sum with a value of 10, which is the y value. However, that is not the case. We need to use match guards here to check manually if the value is equal to y. Because otherwise, we're just creating a new variable which is shadowed. I see what it's saying. Makes sense. But in the second arm doesn't match, yep. Meaning we can use the outer y in the match guard instead of specifying the pattern as some y, which would have shadowed the outer y, and wouldn't have done what we wanted. We specify some n. This creates a new variable n that doesn't shadow anything because there's no n variable outside the match. The match guard, if n is equal to exactly y, is not a pattern and therefore doesn't introduce new variables. Y is the outer y, rather than a new shadowed y. And we can look for a value that is the same value as the outer y by comparing n to y. You can also use the OR operator and a match guard to specify multiple patterns. The match guard condition will apply to all patterns. In listing 1828, we show the precedence when combining a pattern that uses OR with a match guard. The important pattern of this example is that the if y match guard applies to 4, 5, and 6, even though it might look like if y only applies to 6. Okay, so we have the pattern 4, 5, or 6 if y. Right, so if y is true, 4, 5, or 6 only when y is true. Print yes. That's meaningless. The match condition states that the arm only... Oh yeah, it's matching against x. Yep. So if x is equal to 4, 5, or 6, and y equals true, print yes. Right, states that the arm only matches if the value x is equal to 4, 5, or 6, and if y is true. When this code runs, the pattern of the first arm matches x is 4. The match guard y is false. So the first arm is not chosen. Code moves on to the second arm, which does match, and this program prints no. The reason is that the if condition applies to the whole pattern 4, 5, 6, not only to the last value 6. In other words, the precedence of the match guard in relation to the pattern behaves like this. So we have 4, 5, 6, if y. It'll do the pattern first and then the guard secondarily. After running the code, the precedent behavior is evident. If the match guard were applied only to the final value in the list of values specified by using the OR operator, the arm would have matched and the program would have printed yes. The AND binding, the AT binding? That's strange. The AT operator, AT, lets us create a variable that holds a value at the same time. That holds a value at the same time as we're testing that value for a pattern match. In listing 1829, we want to test that a message hello ID field is within the range 3 to 7. We also want to bind the value to the variable ID variable, so we can use it in the code associated with the arm. We could name this variable ID, the same as the field, but for this example, we'll use a different name. We have an enumerable, which has hello, which is a struct holding ID 32. Sorry, it's not a struct. It is a struct, I don't care. Let message equal message hello ID equals 5. Right, matching message on hello. Matching message on hello, where ID is equal to this range. I don't see the at variable, the at keyword. Where's the at keyword? I was promised an at keyword. What are you talking about? This example will print out found an ID of range 5. Yes. It'll match originally here. No, it won't. Never mind. Yeah, I get it. I see it. Yep. Tired. And idiot. I don't understand what's going on though. Using the at to bind a value in a pattern while also testing it. Right. ID variable. Okay. So ID variable is matched to the is bound. ID variable is bound to the value 3 to 7. No, it is not. It is not. ID variable is bound to the value of ID, which matches the range 3 to 7. Okay, I'll not remember that. We're capturing whatever value matched the range while also testing that the value matched the range pattern. In the second arm, well, we only have a range specified in the pattern. The code associated with the arm doesn't have a variable that contains the actual value for the ID field. The ID field's value could have been 10, 11, or 12, but the code that goes with that pattern doesn't know which it is. The pattern code isn't able to use the value from the ID field, because we haven't saved the ID value as a variable. In the last arm, where we specified a variable without a range, we do have the value available to use in the ARM's code in a variable named ID. The reason is that we've used the struct field shorthand syntax, but we haven't applied any test to the value in the ID field in this arm, as we did with the first two arms. Any value would match this pattern. Using at lets us test a value and save it with a variable within one pattern. Okay, makes sense. So we are testing that we have a message of type hello that is in the range of 3 to 7. And separately, we want to have that value used within our expression. So we bind ID variable to the range, to the value in such a syntax. So simply we are having ID equals 3 to 7, but before the 3 to 7, we are creating an ID variable which is bound to the value which matches this pattern. Okay. Using the at lets us, yep. So now we have finally a quiz. However, I'm sorry, but I'm starting to lose my voice, and it's 9:21, so we're gonna have to do this quiz in a week. Thank you so much for joining me, and I apologize for a bit of my tiredness today. I wasn't able to understand some simple concepts that I probably should have, but that's learning, honestly, and that's coding. You're gonna find yourself spending a lot of time on things you probably should know, no matter how good you are. Still, though, once more, thank you for joining me, but this will be the end today. Ah, all right. Why won't you shut off?